On number 14, we're looking at the mean value theorem. So we want to decide if it can be applied to the function, and then if it can, we want to find all values of c such that f prime of c is equal to that average value. So let's go ahead and maybe just remind ourselves what that mean value theorem says, or what functions fit that mean value theorem. So here we want to make sure that our function is continuous on AB and differentiable on AB. So if we look back to that first one that we were looking at here on A, f of x is equal to x to the power of 2/3. This is going to fit that bill. So let's go ahead and find our derivative. So f prime of x. So using our power rule, we can bring that 2/3 down to the front, subtract 1 from our exponent, so that would give me x to the power of negative 1/3. Or really, that's just telling me that should be in the denominator. So I have 2 over x to the power of 1/3. So I want to go ahead then and look at that average value we're kind of looking at. So the f of 8 minus f of 1 all over 8 minus 1. So plugging 8 into my original function is going to give me 8 to the power of 2/3 minus 1 to the power of 2/3 all over 7. So this 8 to the power of 2/3, if it helps, you can think of that as the cube root of 8 squared. So a lot of people don't know how to evaluate that. 1 to the power of 2/3 is a little bit easier. 1 to the power of anything is just 1. But here the cube root of 8 is 2. 2 squared would give me 4. So really we have 4 minus 1 over 7, or a value of 3/7. So I want to take this derivative and set it equal to 3/7 to find that value. So if I take that 2 over 3x to the power of 1/3 and set it equal to 3/7, now we just need to solve for x. So I'm going to go ahead and multiply by x to the 1/3 to get that out of the denominator. And then I'm also going to multiply by 7/3 to move that 7/3 over. All right, so that's going to give me 14 over 9. 7 times 2, 3 times 3 is equal to x to the power of 1/3. So then to get x by itself, we would need to cube both sides. So that would give me x is equal to 14 over 9 to the power of 3, which would give me 2,744 over 729, which is about 3.76 for our value there. If we look at b, b is this function, the absolute value of 5 minus x. So if we think about that, again, remember for that mean value theorem, it has to be differentiable. So if I look at the graph of that 5 minus x and the absolute value, remember that an absolute value function is kind of that V-shaped function, right? So this is just a transformation on that. We're looking at a negative x, and then we have a 5. So just kind of think of the shifts that would take on that function. So that would kind of be that same basic V shape, but we would move to the right 5 units. So this is going to have a sharp point at the value of 5. So remember, it's not differentiable there. So if it's not differentiable, that's not going to fit the mean value theorem, so we cannot apply that. All right, so we don't need to do anything else there since it cannot be applied. So let's go ahead and move on to number 15. So here we want to find where the function is increasing or decreasing. So remember, kind of the first step on that is to find critical numbers. So if we start with part A here, we have x squared plus 3x minus 12. So if I find my derivative, that's going to give me 2x plus 3. So I want to set that equal to 0 and see where it is undefined. This is a linear function, so there are no values where it's undefined. But if I set 2x plus 3 equal to 0, and then solve for x, move my 3 over, it becomes negative. Divide by 2, we see that happens at negative 3 over 2. So that's the value that I am going to then throw up on a number line. I'm going to test values in my derivative to see whether or not it is positive or negative on either side of that, and that's going to tell me where my original function is increasing or decreasing. So if I pick some test values here, let's go ahead and just pick negative 2 and 0. Remember, we test these by plugging them into that first derivative. So f prime of x, which is 2x plus 3. So if we plug in negative 2, I would have 2 times negative 2 plus 3. So that's going to be negative for negative 2. So that's giving me a negative. So that tells me my original function is decreasing. If I plug in 0, that's going to give me 2 times 0 plus 3, so that's going to be positive. So that means on the right side, that's positive, or my original function is increasing. So here we know we are increasing on the interval from negative 3/2 to infinity, and we are decreasing on the interval from negative infinity to negative 3/2. All right, so then let's go ahead and do part B. So in part B, we had the function h of x is equal to the square root of x times x minus 3. And we're only looking when x is greater than 0. That's because our square root part of this is only defined when x is greater than 0. And we want our derivative to also be defined. So that's going to give us the strict inequality there. So the first thing we need is our derivative. So I'm going to need to use the product rule. You can kind of think of your parts as u and v. So I want u prime v plus uv prime. So the derivative of u, thinking of u as again that square root of x, which is x to the 1/2. We bring our power down to the front, so that gives me 1/2, and then we subtract 1 from our exponent, so a power of negative 1/2, which remember is the same thing as a power of a positive 1/2 in the denominator, or a square root. So I'm going to write that as 1 over 2 times the square root of x. I leave v the same, so that's x minus 3, and then plus u, so the square root of x, times v prime, which would just be 1. All right, so let's go ahead and find a common denominator so we can combine these. So I would need to multiply this by 2 times the square root of x over 2 times the square root of x. So that gives me x minus 3 plus 2x multiplying over here. And then this is all over 2 times the square root of x. So then combining our like terms of x and 2x, that gives me 3x minus 3 over 2 times the square root of x. Or we could factor out that 3, just because I know I'm going to find critical numbers, which is where this is equal to 0 or undefined. So looking at those next for our critical numbers, where this is equal to 0 is where the numerator would equal 0. So if I just take my numerator, 3 times the quantity x minus 1, set it equal to 0, I see that happens at x is equal to 1. If I look at where this is undefined, that would happen where the denominator is equal to 0, which would happen if x is equal to 0. But remember, in my original problem, we said x was greater than 0. So this is not in the domain, so we don't even need to worry about this. So then when we're kind of looking at where we're testing to see where this is increasing and decreasing, we can keep all of that in mind. So let's go ahead and put that critical number on our number line. So that was 1. Again, remember, we're not thinking of anything less than 0. So I'm just going to kind of remind myself all of this stuff to the left of 0 is not in the domain, so we don't even need to worry about that. All right, so as I pick my test values, I want to pick something in between 0 and 1. So let's do 1/2, and then something on the right side of 1. And then remember, we're plugging this into our derivative. So that was 3 times the quantity x minus 1 over 2 times the square root of x. And we want to look at the sign of that. All right, so if I plug in a positive 1/2, that would give me 3 times 1/2 minus 1, which would be a negative 1/2 over 2 times the square root of 1/2, which would be positive. So basically I get a negative over a positive, so that's going to give me a negative value. So that tells me that is negative, so I am decreasing on that interval. If I plug in 2, that's going to give me a positive value in the top, a positive value in the bottom, so overall that's going to be positive. So if my derivative is positive, that means my original function is increasing. So when we are looking for where our function is increasing, we know it's going to be increasing from 1 to infinity, and we know it will be decreasing on the interval from 0 to 1.